All right, thank you, Yafe, for the introduction. Good morning, everyone. I hope all of you are enjoying our little workshop. Certainly, I am. My name is Bishwajit Dotto. Currently, I'm a postdoctoral researcher at the City University of New York. I'm also the chair for today and giving the first talk. And if you see too many CrSBr talks, you know who is responsible. Anyway, I'm very excited to talk about our ongoing work on strong light matter interaction in CrSBr. So the work that I'll be presenting today is led by another postdoc, Pratap, me, and a graduate student, Sichao. And on the very left is my postdoctoral advisor, Professor Vinod Menon. We have also collaborated with other people for this work. We have collaborated with Professor Andrea Alu's group at City University of New York. And we get our very nice, high-quality crystal from Prague, from Professor Sofer's group. And for theory calculations, we have collaborated with Swagato and Mark from NREL and Dimitar from King's College London. Now, there were already quite a few talks on the first 2 days on CrSBr, so I'll keep the introduction short. Just to jog our memory, CrSBr is a layered antiferromagnet. The reason we are really interested about CrSBr is we can both probe it optically and electrically. Unlike many other semiconductors, that turns out to be very insulating at low temperature. For CrSBr, the resistance still remains measurable at few Kelvin temperature, and hence very interesting for experimentalists. Also, unlike other 2D materials, this remains direct bandgap for all thicknesses. So students like us don't really have to spend long time exfoliating thin layers. And also, it is an air-stable material. So CrSBr is a semiconductor, so it hosts excitons. And it has been shown in literature that the energy of the excitons can be nicely tuned with an external magnetic field. Since in addition, it's also a magnetic material, it also hosts magnons. And people have measured magnon dispersion over the entire Brillouin zone. But really, what people like about this material is the coupling between exciton and magnons, and the fact that you can study the magnon dynamics just with optically probing it. Now, in our group, apart from doing spectroscopy, one of the major focus is to study strong light matter interaction in cavity. And Florian actually, when he was in New York, led this beautiful work where he showed that the A exciton of CrSBr, or the exciton that we all heard so far, has very nice oscillator strength that it can nicely couples to the cavity mode. And like excitons, you can also tune their energy of the polariton branches with an external magnetic field. So most of the studies that we have seen so far focuses on this exciton, A exciton. This is the lowest lying exciton in this material, and also happens to have the largest amount of oscillator strength. However, what I'll be focusing today is another exciton, a higher energy exciton. And hopefully, I'll show you that this is not like other materials. For example, TMDCs, you also have A and B exciton, two excitons. But in many ways, they are similar. In CrSBr, on the other hand, we'll discuss that A and B excitons have very, very different properties. And that is why B exciton is interesting in its own right. So what do? We, to begin with, take these materials and exfoliate them down to not necessarily thin layers. Thanks to the anisotropy, these crystals, when you exfoliate, they always come in the form of a rectangle. So the long dimension is aligned with the A crystal axis, and the short dimension is aligned with the B crystal axis. So this is our differential reflectance measured at 4 Kelvin. So we see two curves here. the solid curves corresponds to light polarization parallel to the B axis of the crystal. And the dotted line is the differential reflection for light polarized along the A crystal axis. So for the B polarization, we see two spectral features here. And the feature at around 1.32 electron volt corresponds to the A exciton that we have seen so far. And there is another feature just a little bit below 1.8 electron volt, and that corresponds to the B exciton I'll be focusing today. Our calculations show that A exciton has around 0.75 electron volt binding energy, and the B exciton has around 0.25 electron volt binding energy. We can also detect photoluminescence from both of these excitons, but since the B exciton is higher up in energy, the photoluminescence is very weak. However, the B exciton is also polarized along the same direction, the B crystal axis, like the A exciton. One of the interesting observations from this data is you see the high shift between the absorption feature and the photoluminescence peak. And this is called a Stokes shift. So for B exciton, you have noticed that the Stokes shift is rather high. It's almost 100 MeV. For the A exciton, the reported Stokes shift is of the order of 10 MeV or less than 10 MeV. So this is an order of magnitude enhancement in the Stokes shift. While we are not at the moment fully sure the reason behind it, one idea is it could be because the exciton phonon coupling might be higher for the B exciton compared to the A exciton, and that might be reasonable behind this large Stokes shift that we observed. So since we are talking about the higher energy exciton, which has almost 1.8 eV energy, it probably we'll probably spend a little bit amount of time talking about the band gap of this material. And this is where the literature has all sorts of values, and it's a little bit debatable. For example, if you start with the first report from Columbia, where they measured the band gap by doing STM measurements, and from the STM measurements, they ascribe a band gap of electronic band gap of 1.5 eV. There were a few other papers, papers published after that quote similar band gap, but more recent calculations show the band gap is probably closer to 2.1 eV in this material, which is much higher than 1.5 eV. From our experiment, what we can say is, since we are working with 1.8 eV exciton and we can nicely form exciton polariton, we know it's a positively bound exciton, and so the band gap is certainly more than 1.8 eV, and if our calculations say the binding energy is 0.25, so we think the band gap is closer to 2.1. So as I said before, even though there are two excitons, A and B excitons in this material, unlike TMDCs, they have very, very different properties. For example, if we see what orbitals are responsible for A exciton, we see the dominant contribution actually comes from chromium on-site orbitals. So that means A exciton is very, very localized in real space. Or in other words, it's more Frankel-like. B exciton, on the other hand, the dominant contribution comes from chromium intersite. And that makes B exciton much more delocalized in real space. Or in other words, it's more one-year-like. This is our calculated band structure, and the calculations were done by Shagata, Mark, and Dimitar. And what we have done here is we have highlighted the states that are involved in making A exciton. And you will see that for A exciton, more or less all the momentum points are involved. For B exciton, on the other hand, we see it's primarily momentum close to the gamma point that are involved in making the B exciton. So this is fully in agreement with the fact that A exciton is much more localized in real space, and B exciton is much more delocalized in real space. So the B exciton that way behaves closer to TMDC excitons. So one of the selling point, and people are very excited about this material, is the exciton and magnons are coupled, right? So you can apply an external magnetic field to change the energy, and for A exciton it has been shown. So you have done similar measurements for the B exciton. So we have what we have plotted here is the differential reflection as a function of energy in the x-axis and magnetic field in the y-axis. And here the magnetic field is along the a-axis of the crystal. So we see a parabolic feature. That's because the exciton is highly dispersive with magnetic field. And extracting the dips, we see that in the ferromagnetic state, the energy of the B exciton reduces by 80 MeV. If you compare this shift with the A exciton, for A exciton from the literature we know that the shift is around 16 MeV, and our data is in agreement with that. So we see that B exciton shifts almost 5 times to that of A exciton, and the question is why? Why is it more sensitive? So we have numerics to support our observation, but before we go there, let's intuitively try to understand what's happening. So here we have plotted the wave function of the A and B exciton in the antiferromagnetic state. So there are 2 key observations from this data. First of all, right away you can see that the B exciton has much more Bohr radius compared to A exciton. It's roughly 4 times. A exciton is very localized, around 1 nanometer Bohr radius, and according to our calculation, B exciton has around 3.5 to 4 nanometer Bohr radius. Also, we see both the A and B excitons are only localized in 1 layer, so their wave function don't really spread over many layers. Now in the ferromagnetic state, we see that the A exciton remains as it was in the more or less AFM state. The wave function does not spread in the outer layer. However, for B exciton, here we had to cut short the calculation because it was expensive. If you choose the unit cell even more, you will see that the B exciton will delocalize more even along the B axis. But what I want to point out here is the C axis, along C axis, and you will see in the ferromagnetic case for the B exciton, the wave function starts spreading in the adjacent layers. So intuitively you can think that the quantum confinement for the B exciton reduces in the ferromagnetic state, and that redshifts its energy more than it does for the A exciton. Now coming back to the calculation, our calculation, again the calculation was done by Shagata, Mark, and Dimitar, and it's QSGW calculation, quasi-particle self-consistent GW calculations. You see that I'm struggling to remember the name, so please don't ask me any more questions on that. So we see around 2.1 electron volt of band gap in the antiferromagnetic state. When we increase the external magnetic field, it goes to the ferromagnetic state, and we see the band gap reduces by 100 milli-electron volt. Now, if nothing happens to the exciton binding energy, we would expect that the exciton binding energy will reduce, the exciton energy will reduce by the same amount, 100 MeV. However, from literature, we know for sure that's not the case. The exciton energy for the A exciton reduces by 10 milli-electron volt in the ferromagnetic state. So what happens is, in the ferromagnetic state, the binding energy of the A exciton also reduces. And when the binding energy reduces, the exciton actually moves closer to the band edge, right? Partially cancelling out the redshift of the conduction band edge. So to be quantitative, our calculation shows that A exciton binding energy reduces by 90 MeV, conduction band edge moves by 100 MeV. So the net redshift for the A exciton is 100 minus 90, 10 MeV. For the B exciton, on the other hand, and this is where the difference of A and B exciton comes, the B exciton does not follow the exact same trend. The B exciton binding energy reduces much lesser. It reduces only by 34 MeV. So the cancellation of the band gap reduction of the conduction bandage redshift and the binding energy reduction is not full, and hence the B exciton reduces, energy reduces much more. So to be exact, 100 minus 34, 66 MeV. Now, in experiment, we see the B exciton reduces by 80 MeV, and the A exciton reduces by 16 MeV. So the theory numbers are not exactly matching the experiment, but that's for our theory colleagues to blame. So far we have discussed this exciton, a new kind of exciton that's more one-year-like, and we have shown that using an external magnetic field, we can change its energy a lot, 5 times of that of A exciton. The question is, can we do anything useful with it? And as I said before, in our lab, one of the primary focus is to study strong light matter coupling inside a microcavity. And I don't really have the opportunity to go into the glory details of microcavity physics here, but very briefly, what we do is we take a dielectric Bragg reflector mirror, and we put our material of interest, and then we deposit a top mirror. The distance between the two mirrors selects the cavity mode, because you have 2 mirrors, light gets confined, and if we reduce the distance between 2 mirrors, then the cavity mode blue shifts. So we choose the cavity length depending on our exciton resonance, and when the cavity mode is in resonance with the exciton mode, they can further hybridize with each other and give rise to new modes known as lower polariton and upper polariton. Now, one of the great advantages of using such a microcavity system to study exciton polariton is just by tuning angle, you can smoothly go from a very light mode to a very matter-like mode using the same system. Now, in polariton physics, one of the key external parameter that is very important and determines all the properties of polaritons is the cavity detuning, which is basically the energy offset of the exciton energy compared to the cavity energy at 0 momentum. Now, typically, this depends on the design of the cavity. That means if you want a different detuning, you really have to make a different sample where you change the cavity length. Now, here, exploiting the fact that we can change exciton energy by a large amount with an external magnetic field, we have realized in situ tunable detuning. That means we can go from a negative detuning. Negative detuning means the cavity is below the exciton energy, to a 0 detuning where the cavity mode and the exciton modes are resonant, to positive detuning where the cavity mode has higher energy compared to the exciton mode in just one system. And this is really an important knob for systems like, for example, polariton condensation, where you really change the onset of the condensation and everything with just this single parameter. So this is our experimental data where we have taken such microcavity, and we have tried to couple the B exciton with the cavity mode. And the magnetic field is along the C axis of the crystal. And we can clearly see 2 polariton branches and a large avoided crossing in between that. So now here I'll show you this same data for a couple of different magnetic fields. And it's not really surprising to see the polariton branches moving with the magnetic field, because the exciton resonance itself moves. However, you will see another interesting thing is that when you change magnetic field, not only does the polariton branches change, also the number of polariton branches change. For example, at 0 Tesla, we see 3 branches. At 1.75 Tesla, we see 2 polariton branches. At 1 Tesla, we even see 4 different branches. So to see it a little bit better, we will take a line cut of this data at a particular momentum, which is the x-axis. Yeah, probably I have not explained this. Such a data is analogous to band structure. The y-axis is energy, and the x-axis is momentum. The only difference is here we are plotting the momentum of photon, which is way lesser compared to crystal momentum. So when you take a line cut at a particular momentum and plot the differential reflectivity at different magnetic field, we can see all the different polariton branches, and I have connected them with dotted lines. And we can see that for some magnetic field, we see 4 dips. For some magnetic field, we see 2. And for some magnetic field, we see 3. So we can also plot it in a color plot like that, where the y-axis is magnetic field, the x-axis is energy. And these are the branches. So in our cavity, we have one photon branch. So to have 4 polariton branches, you will need at least 3 excitonic resonances. So what's happening? Just to remind, when we did the reflectivity measurements for the B exciton, without the top meter, without the cavity, we just see a broad dip in the reflectivity that corresponds to B exciton. So how do we explain these 4 different branches? And what we think is happening is the FWHM for the B exciton is broad compared to A exciton. And we think that there are close by resonances, and we cannot really pick out individual resonances without cavity. And what cavity does is it enhances the contrast of some of the excitonic transitions, and that is why in the cavity you can see 3 different excitonic modes all coupled to 1 photon mode, and hence 4 polariton branches in total. So here our optical cavity actually helps to pick out individual excitonic transitions. So with that, I will summarize my talk. So in our talk, we discussed a new exciton in the same CrSBr. This exciton is very different than the A exciton. It's 1 year-like. Its bore radius is much larger. We have shown that this exciton is very, very magnetic field sensitive. In our, to our knowledge, this exciton surpasses any other excitons in any other material with 80 milli-electron volt shifts per 1 Tesla magnetic field. Using this large shift, we have realized a negative to 0 to positive detuning all within same cavity. And optical cavity also helps us to put more light into how this B exciton is made up. Probably there are more excitonic transitions close by that we cannot pick out without optical cavity. And lastly, B excitons also show a large Stokes shift compared to the A exciton. While we have to confirm this by calculations, we think that B exciton possibly has a large exciton-phonon coupling. With that, I conclude my talk here, and thank you for your attention, and welcome any questions you have.